Let's look at random number generation in SAS. So suppose I have a data set that I want to create with 3 variables that are all uniform random variables, and I want to create a sample size of 5. So I'm going to run this do loop, do I equals 1 to 5, and create each of these 3 variables every time, and then output. Remember, if I don't use this output statement, I'm going to end up with a data set with only 1 observation in it. And then to start this random number generation, you always need a seed in any computer program that you run. If you put 0 in here in SAS, what that means is it will use the computer clock to create its seed. So you'll have a different data set every time you run this program if you put zeros there. On the other hand, if you put your own seed in, you'll get the same data set every time this program is run. So I'll show you what ends up being. So we have this seed, seed 1, seed 2, seed 3, and then these are the variables that we created. If you want to, on the other hand, use some other kind of seed, you can get SAS to generate you a seed from your seed, if that makes any sense. So I'm going to start out with seed 1, 2, 3, 4, and this call function will tell SAS to use that seed, the 1, 2, 3, 4, to create its own seed, and then use that seed to generate a random uniform number. So it's a little bit messy, but it gives you one more step away from your own seed that you created. So you can see these are the seeds that SAS is using, and then those are the 3 variables that you came out with. As long as you keep using these same numbers, 1, 2, 3, 4, and so on, you can run it again and end up with the same data set every time. So it's another way of getting the same data set. Here are a few more random number generators. You can use the binomial seed. You need to go ahead and specify N and P, the parameters for the binomial. The exponential will give you an exponential with mean 1. Normal, this is a normal 0, 1, standard normal. Poisson will give you seed. You have to specify M, the mean of the Poisson distribution, and then our uniform 0, 1. So here's a similar function. It's just a little bit different way of reading the random numbers in. So here we use the ranunif function, and then there's a ranor function, a ran exponential function. But here, this is just the rand function. It will generate you a random number from the distribution that you specify. You can specify normal, that'll give you normal 0, 1 again, and then I've got a list of different distributions you have here. You don't have to use all those letters there. You can just use the first 4 letters of any distribution. I'm just being complete there so everybody understands. Then again, just like we used that call function a minute ago to call this to get our own seeds, I can call stream init, and then I put a seed in there, 1, 2, 3, and then when we run this, we end up with the same function, the same data set every time we run it. Because we were using that call function, it gave us a new SAS's same seed every time it runs. However, if you put that as a comment, in other words, if you don't run this call statement, you're going to get a different data set every time you run it because, again, it's using the clock as the seed. So if I run this again, you can see I got a totally different data set. So use that at your will. This is an example of a program that double checks to make sure that the t-test is actually giving us p-values that match the t-distribution. So suppose I'm going to randomly generate this set of normal data. I start out with a random normal variate, and then I multiply by sigma and add mu to get this normal 10, 2 distribution. And then I'm going to create a sample of size 10. and then I can print that out. You can see my x's should be normal with a mean of 10 or so. It looks pretty good. And then if I create a new variable that has x new is x minus 10, that variable should have a mean of 0. So then we can run this Prati test, which has the null hypothesis that the mean is 0. And I should get a p-value that's bigger than 0.05 most of the time, although here I got a p-value of 0.02. Most of the time, though, one time in 20 it should be below 0.05, but most of the time I should be good to go. If I run the program again, create a new data set. This time you can see I did get a p-value greater than 0.05, although it's a little close for my comfort. So I might want to go back and see what's going on. It looks like something might be happening. And here's an example of a linear regression procedure. So suppose I picked out my intercept and two slopes, 0.3 and 3, and then I got a standard deviation for my errors, which is pretty big. N is 20. And then I'm going to do I is 1 to n, x1 is I, x2 is I squared. And then I'm going to multiply b1 by x1 and b2 by x2. And then I can go along and double check to see if my model actually gives me what I would expect, the 0.3 and 3 as my x1 and x2. 0.3 looks a little far away from what I thought it would be, so maybe something's wrong with my program. Maybe this doesn't really have the distribution that I thought it would. So that's the idea in simulation, is to see if things really have the distribution that you think they would. And you can put these programs inside macros. See how we only ran the Prati test twice. You can put this whole thing in a macro and do it 100,000 times and get a whole bunch of x news to see whether or not things have the distribution you expect they would.